everyone. My name is Fred. So today's session, we just started. Today's session, we're going to have an introduction to Parallel Fortran and Gadi. This is going to be quite a small, casual session for two reasons. One, this is new material. The NCI training team compiled this material recently due to demands for Fortran training. B, because it's a new session and we also didn't advertise very boldly, so it's going to be quite small. I think now have 12 people in the room, 13 about to join, excluding me, and in the background is training team manager, Abdullah. So probably around 10 of you in the session. So feel free to ask any questions. A little bit about myself. My name is Fred. I've been with NCI for 4 years now in this training space, mainly delivering training in parallel computation, high performance computing, particularly related to scientific programming using tools such as MPI, OpenACC to accelerate code. And who am I to teach you Fortran? I'm not a Fortran expert, so I would not claim that at the beginning. I have been working on Fortran code during my PhD time as one of my side project was Earth seismic wave simulation code. The code was a well-written parallel Fortran code, and helped to optimize the code, implement some new features, and offload it to GPU using OpenACC. So I have some Fortran. So yeah, that was my Fortran exposure. So today's focus won't be teaching, won't be like a course to teach you language concepts in depth. It's not going to be like university type of Fortran course. And I assume some of you probably have already been writing Fortran code for some years. So you probably know more of those nitty-gritties about Fortran than I do. So the focus of this course is about when you have a Fortran code and how to port on Gadi and how to run that on Gadi. So that will be the focus of this course. But nevertheless, if you are new to use Fortran, as far as I understand, not many universities teach Fortran these days. Really, outside the scientific computing community, no one really know what Fortran is. Even they know Fortran, even they do, they would think Fortran has been basically died out for years. This is literally what I heard when I was in one of the computational maths conference a few years ago. Even in the computational maths community, some people literally thought Fortran is just an ancient language and no one used them anymore. However, if you are in scientific computing, morning all, thanks for joining. I just realized a few more people joined. I was just give the introduction about what the scope is for this session, and a bit background about Fortran, in case Fortran is new to you. So I was just saying, even within the scientific computing community, as far as I know, it is very fundamental, but it is not well taught language, just because I guess no channels, there's no venues to teach them. Like it's not like Python, right? Like university courses teach them. We'll see. It's been around for many years, but the from my own experience, learning Fortran is always bit of a niche thing. Like the chances are you start working on projects and realize then you inherited with the legacy code which is being written in Fortran. By the way, this Fortran we're going to be modern Fortran. It's not going to be Fortran 77 Fortran. So if this is why you're after Fortran 77, no, maybe it's let me know. But you might not find this material is super related to you. So this probably should be bracket here parallel modern Fortran on Gadi. Um, um, so um, um, modern Fortran will be the focus of this course. If you just inherited some legacy code and try to learn Fortran, and this is the course that we sort of designed for in a way. We'll talk about scheduling in a second. I think I'll probably give it be too detailed introduction at this point. So let's move on. Acknowledgements of the country, the National Computational Infrastructure acknowledges, celebrates, and pays our respects to the non-white and Lambe people of the Canberra region and to all First Nation Australians on whose traditional lands we meet and work and whose cultures are among the oldest continuing cultures in human history. Indeed. So I was talking about schedule. This is scheduled for 2 hours, but I'm trying to make this sweet and short. So I don't want to get us bogged down into too much programming concepts and stuff. So we will spend probably first 40 to 50 minutes go through Fortran basics, just in case some of you may find this is fairly new content and you want to just get synced with write basic Fortran code. So we'll go through some of that programming syntax perspective. Then we're going to take 10 minutes break. Then we come back. We will do one simple code, a simple scientific programming code. It's not going to be as simple as Hello World. You're still going to use the MPI. So we'll have a look at that code, which is going to be Monte Carlo simulation code. The code is being provided to you, and the code has two versions: CPU version and GPU version. There's no code I call it exercise, but there's nothing required for you to code. This is not going to be a workshop and ask you to do exercise questions, stuff like that. I'll just showcase you, demo to you how does Fortran work well with the parallel support, IE, I guess, MPI and NVIDIA's OpenACC support, and to compile this code on the machine on Gadi on supercomputer, and how to run the job on supercomputer. So this will be the second part of this webinar. Any questions so far? Feel free to unmute yourself, ask questions at any point. It's not super important for me to finish everything today. It's probably more important for me to understand your problems during this session. Yes, I'll pause for a second in case there's any questions or anything, or I didn't make sense about any parts. We're all good? Okay, so the materials, you might want to actually put this link in the chat, so you can get all the materials for this session. So all the code is there. So I don't think it's all the code is there. And this GitHub repo, and inside that repo, I'll show it here. Once you inside this repo, this intro parallel Fortran. So you have the code for second part. First part, we're gonna use this documents to go through the language syntax. Sorry, I didn't get it short. Sorry. If you click that link, it is here. Sorry, I realized that might not be shown on the screen. Can everyone see my screen? About the GitHub page right now?
Yeah, can see.
Sorry, thank you. So link is in the chat. You can click this document page that goes to this document. Okay. Let me know if there's a problem with that. And just quick overview. So I think I talked a bit about this already. What we're going to focus is we're just going to focus on compiling and running parallel modern Fortran programs on Gadi. Also, I kind of assumed everyone knows what Gadi is, since I put in the title of this session already. It's the supercomputer that we provide at NCI. So we want to go through, introduce this topic related tightly with the infrastructure that we provide to our users. So we'll look into the basic language syntax, learn array box features, which is quite a very unique feature of this language. And compile with the Gadi supported compilers. However, this is not a programming language course, so we don't cover programming concepts in depth. Okay. We're clear with that. Let me zoom in here. So we'll go through the session. So yeah, this document is short, as I mentioned, introduction to Fortran, modern Fortran for scientific computing. And then we go to tutorial, and programming basics. Okay. So we'll cover Fortran programming basics, compile and run parallel Fortran code on Gadi. If time allows, we'll have some live demo on compiling Fortran code. Okay. So why Fortran? I guess be a motivation. I mentioned before. Why we care about Fortran? I guess you made your way here. You're interested already, but also maybe you just needed to work on Fortran code, and you just have to pick it up. And without understanding much appreciation why this ancient language I still need to learn, and which basically you don't see it anywhere else outside of scientific computing. But if the scientific computing is your business, you probably you're probably aware that Fortran as a language is really simple, or I won't say really simple, but it's compared to C, it's very much easier to use for scientific programming. For its, I think one main reason has been, later we'll talk a bit more about this, is it's sort of like MATLAB, and everything is provides the array and the matrix operations. It provides many language supports around those objects. So I kind of like to compare to MATLAB, just how it operates. And and it's open source rather than MATLAB is commercial. Another perspective, Fortran was still very prevalent and important in scientific computing is it has it is the first class citizen in terms of parallelization support. So the de facto parallelization tool MPI that has its standards has only two native support. One is C, and another one is Fortran. NVIDIA GPUs has the compilers also supports Fortran, and it's or the OpenACC. Those from OpenACC, which is the multi-threading acceleration through GPU, also provides native support for Fortran. And then many underlying scientific libraries were in the first place written in Fortran as well. For example, the BLAS libraries, so the low-level matrix vector operation libraries, they were written in Fortran. So inside scientific computing, Fortran is a very well-supported language. And again, its language is fairly much less complicated than C++, and it's kind of is designed for scientific computing. So some prerequisites before we move on. Well, hopefully you have that. Is comfortable with command lines. Later on, we will compile Fortran. Fortran on Gadi is through GCC, which provides you GFortran. You have an Intel compiler as well. In the classic, is iFort through Intel compiler with all the intercompiler modules. This is classic one. The Intel Fortran IFX is the later modern version. I would say it's a later version, newer version of a compiler through Intel compiler LLVM modules. Parallel compiler wrappers MPI F90 is you have this through both OpenMPI or Intel MPI modules. We recommend users using OpenMPI for parallelization code on the machine. So at this point, I think I'll just quickly do a quick demo, show you this compilers, where to find them. Oops. On Gadi. So if you are a Gadi user and in the terminal, you can do the same thing. Just check on the same thing with me. Again, everyone can see my screen. I take silences. Cool, sweet. Yes. Thank you. Okay, so if you're an NCI user already, then I will not go and assume you know if you've been to our intro to Gadi session, which is another session I ran. We talked about modules. This is how we load some different applications, compilers on Gadi. Module avail. So module avail gives you all the centrally supported libraries. So what I mentioned was, I think even just 3-5 years ago, like Intel, if you compiled Fortran with Intel, this is the compiler you would use, Intel -compiler. But all the latest, Intel has moved to one API now. So they have their new compilers is through Intel compiler LLVM. So if you do GCC module Fortran through GCC, build GCC. You have the GCC versions. Excuse me. Sorry about that. Module load GCC, and it will get you G Fortran. So which G Fortran? Excuse me. Let's the HPC in Canberra. Oops, sorry. So it gets the G Fortran from the module we loaded. So if you IFX, there's no IFX, it's the Intel Fortran compiler, then you will need to module load Intel compiler. Usually we just do for Fortran compiler, I just loaded the latest version. Then you get the Intel Fortran compiler. But again, we prefer well, I guess if you're running code on Gadi, you probably would have an MPI Fortran MPI code. In which case you will need to load the MPI compiler wrapper. So let me module loads. So for the MPI, again, you have two MPI wrappers provided on the machine. One is through OpenMPI, one through Intel MPI. Let me show you OpenMPI first. So we have all the OpenMPI versions. Again, we recommend you use the latest version. Module loads open. So now you load this in the now you compile is MPI. I'm sorry, MPI Fort. This all Fortran compiler with MPI wrapper for Fortran compiler, which includes the MPI library loaded. So what this is, it is a wrapper. It says, okay, your underlying compiler is Intel compiler, so it's going to use IFX and with the MPI flags to use MPI libraries. Okay. However, if so module now I'm going to unload this. If you want to use Intel MPI, so it's through Intel MPI. So I have all the Intel MPI versions. It's through this one. Module loads. Now your MPI force. It's going to be yeah, now it's through Intel MPI. So if you do Intel MPI, then there's going to be MPI F90. We recommend you use OpenMPI on the machine because for the Intel compilers, they are shipped by binaries, whereas on the OpenMPI, we built from scratch and is optimized based on the machine. We'll come to be more details how to use the different compilers later to compile the code. But for now, just show you where to find the different compilers on the machine. Any questions so far?
Yeah, I have a question. If you want to compile F77, like Fortran 77 legacy code,
Yeah,
what do you do?
I believe will be F77. Um, so I so I well I don't work on F77, but I believe you still use the same compiler, but the compiler will pick up your format. If it's
Yeah.
F, yeah, we'll just pick up the format.
Oh,
Based,
that's fine. I just needed to know the command. That's great. Thank you.
yes, right. Yeah, command is the same command. In other machines wrapped up for you for MPI F9. Yeah, it's a wrapper. It wraps the underlying compiler. Okay. Again, I'm sorry. This is not going to be a F77, which yeah, it still exists, I suppose. Okay. So check installation. Well, just check out the machine, G Fortran version. So Fortran has some multiple versions, as I mentioned here. So there's a quite simple command. If you have hello world code, which if you have hello world code, it's very close to C compiler. Yeah, so G Fortran or IFX with but do mind that they have different flags though. So the GCC compiler and the Intel compilers, they have different their flags, and they are usually not. Sometimes they are not one-to-one correspond to each other. I'll see if there's a question in chat. Okay. So so Fortran Fortran comes with different versions, and that every version has different features. 1995, 2003, and 2008. I'm not sure if there's probably later version as well. They all use the same format F90, so pretty much the compilers you use these days all support 2008 features, and it's all backward compatible. So just don't be fooled by the formats.f90. It actually what it tells us it's not F77. It's what it means. It's basically treated as the modern Fortran delineate. And the compiler will pick up all these the features from different versions. But again, basically all the compilers you use on our machine supports the latest features, and it's all backward compatible. So yeah, the modern Fortran version doesn't really matter here. In as far as our compiler concerns. So just hello Fortran. One simple, I guess one of the main things about modern Fortran is its free format, which we'll see a bit later. That's when it starts to be called modern Fortran. So the simple hello world code here. In modern Fortran, I have an implicit none here. This is telling the compiler that disables implicit typings and catches many bugs in the compile time. So without it, the Fortran compiler will interfere, will infer the variable type based on the name, and then with a name with a very interesting rule, which I don't remember on top of my head. So basically, I think it's if your variable name start with certain letters, this thing is integer. Start with other letters, you think it's a real real type. So to disable that, you need to put this implicit none at the very beginning of your program. Then tells that then tells the compiler that the user will define explicitly for the data types for your variables. So this is very important thing in modern Fortran to include this one, implicit none. So source form, I kind of mentioned about this freeform source. The F90 is standard in F95. So that means well, the format there's no strict format in F9 in modern Fortran. All the comments start with the exclamation mark. Indentation is for human in modern Fortran, not for the compiler, but keep it consistent. I guess that's good. Simple, good programming practice. Types and declarations. So they're building numerics and the logical types. The numerics integer, this basic C integer. You define it with the type, followed by 2 semicolons and what variables they are. They have real as well. So real in Fortran is a single position, so 32 bits. If you need 8 bytes, 6 double precision, 64 bits real. You need to use this keyword kind. So this is defined numeric types using this defines numerical numeric types. If you want a double position like in C, then you increase this to 16 bytes. So logical is just the Boolean. You can give the two variable names. The character you define character is like char in C, and with a bracket you can specify the length of it. And use parameter for constants, much like the constant in C or C++. So in most when you actually program Fortran, you probably want to predefine your a precision and use the same precision throughout the code. For example, what I did here is define a working position first, which is a select real kind. So this is going to be 15 decimal to exponents 99. This can represent numbers that has 15 decimal to exponents to from minus 99, so as small as minus 99 to 99. And then you can use this working position from that point down so basically like customize the defined precision. You can use this precision for all your other variables. For example, here I define as a working position. So this with this underscore WP, this again custom. Just be reminded that this is not a built-in thing. It's what I defined before. But with the underscore WP, the syntax, it enforces this position to be the working position kind. You see this quite often in Fortran code. Okay. Any questions so far at this point? Okay. We'll just crack on. Again, this syntax part is probably going to be, for some of you, it's quite basic. But I just want to get everyone on the same page, so I'm going to go through this with a steady pace. So arithmetics, plus minus times division and the power. relationals, equal, not equal, less, greater, greater or equal, so on and so forth, logical, dot, and dot, or dot, not dot. They are the same logic. They are the logic that you can imagine what they are, just with its own syntax. So nothing much to talk about that. This just for your information if you didn't know that before. Input and output, least directed I/O. So the print statements in Fortran is much simpler than C. So because it's in more than Fortran, I should say, because it's a free form. So what I mean is that we start with the keyword print with asterisk mark. So this is indicating that there's a free form, and you just put your string there. If you want to have a variable, then you just separate it by a comma with your variable. So it's free form, very, very easy to use. You want to format it, that's okay. A string start with A, and you can then you can specify the field width and how many decimal decimal star for that value. That's one example here. If you want to do file I/O, I didn't include here. Then Fortran, it kind of like Python, I guess. You open a file and there's function for the write, then you write it down in the file. So it's all user friendly. Control flow if and case. You have an if case here. So read is read user data against freeform, but you have to define this variable first. If then just if condition based, it's the same as C or Python. C or Python. If else if the only thing is you have to end the block with the end if. So this I guess one difference from the C. You have cases as well. With the select case, it's kind of like C as well. You have case. In the case, you can say you can put different matching case. So in this case, if it's lowercase y or bigger case y, the all prints yes. If lowercase n or capital case n, it's all prints no. Okay. Again, you have to end this block with end select. Loops. The syntax is do. Fortran is the index start with 1. So I was told this probably anecdotal, like if the program language is invented by a mathematician, it will start with the 1 natural number. If it's invented by a computer scientist, they start with 0, such as Python or C. MATLAB and Fortran, they start with 1. So I thought that was funny. The do loop, just if you're familiar with C, it's kind of similar, I guess. It's your variable, your starting point and end point. Starting indexing and end indexing, and do to enter this for loop. Use exit to break and a cycle to continue. So I guess in C that would be. I use a lot of like C analogy here, just in case. Well, I think C is also because C is just popular language in scientific computing. So just to sort of build up that relation. But if you're not familiar with C, then just ignore when I start the sentence with in C, blah, 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 blah. So in C, I guess it's break is break, continue is continue. It's just important. It's exit break, cycle to continue. So far it's all simple stuff. 1D arrays and array features, declaring arrays. Array is much easier in in Fortran than in C, which is because arrays really insists of associated with pointers. Then you start having all sorts of rich features / complexities in C with arrays. But in Fortran, array is just mathematically array or like a MATLAB. You can define with a fixed size, data type, A is array, the length of the array, fixed size of the array. This 1D array, and we can define 2D array as well. If you wanna initialize the array with variables or with values, you can use you just use the square bracket / or your values close with / bracket. In modern Fortran, it's probably easier to do with just square bracket, kind of like again MATLAB. In Fortran since 2003. But again, as mentioned before, all the compilers, Fortran is backward compatible, and all the compilers supported the latest version. So you can write the code with the latest version, and they will compile on Gadi. It has a whole array operation, kind of like Python. So this is a very nice intrinsic feature of Fortran. This would operate on the entire array. Be careful though. This square bracket only creates 1D array. If you want multiple array, you need to create them and then reshape them. Kind of like Fortran and Python, NumPy. I guess NumPy is fairly close to what we see. NumPy arrays is kind of fairly close to what Fortran arrays is like, if you have that bit analogy. Fortran is famously, I mentioned at the beginning, what makes Fortran special or like very favorable in scientific computing. One reason is famously optimized for linear algebra and scientific computing. So unlike C or Python, where multi-dimensional arrays are often listed or lists. Well, I guess the caveat here is when I say Python is not seeing NumPy. NumPy is NumPy arrays. I think underlines calling Fortran functions. So that's why I said like NumPy is very close to Fortran. So Fortran arrays are first-class citizens with built-in support for matrix arithmetics, slicing the memory management. So it's quite easy, nice and easy to work with the Fortran arrays. We'll go through a bit more details about the arrays because it's just an important aspect of Fortran. So in Fortran, the number of dimensions is called the rank. Arrays can have up to 15 dimensions in modern standards. Rank 2 is matrix, and rank 3 cubes are probably the most common ones. For example, how do you define a matrix with any arbitrary size? Say if in this program it's implicit. Again, just put the implicit noun at beginning of your program. It's not, well, if later in some cases you put after some other some things, but it's usually like at the very top of the program. Right, so matrix. If you create an integer matrix 3 by 3, then it's like NumPy, just with NumPy, just with the explicit typing integer matrix 3 by 3. If you want a rank 3 tensor and tensor 10 by 10, yeah, it's just what you would imagine. Alternatively, you can declare using dimension attributes. So here's a real type matrix with dimension 5 by 5. So nothing surprising there. It's 10:15 now. I'm probably just gonna park here because due to the schedule. Gonna take 10 minutes break. And then we'll come back to go through more. I'm probably be behind the schedule. I'm be behind schedule. Is it okay we take just 5 minutes break?
Sure.
Sweet. Take 5 minutes break, get a cup of tea, and then we'll come back and crack on these slides before we return to more interesting hands-on demo.
Fred, just before you break, there is a question in the chat
Oh,
about
yeah.
the difference
Yep. Thank
between
you.
assignment with parameter or without.
So assignment with learning. I'm just reading. What is the difference between assignments with parameter keyword and assignments without? So parameters for constants, right? So if by the way, it's just taking a break, and or during the break I'll answer questions. So feel free to take a break if you decide. So in Fortran, the parameter attributes is different from between creating variable and which can change. Let me word this correctly. So with what we talk about here is a parameter for constants. So this means this cannot change. So when you write integer parameter n equals 10, so you are creating a compile time constant. That means you can't change that variable. And if without it, then you can. I guess did I get a question correctly here? I guess you're talking about these assignments here. This is what I use assignments, parameter in the assignments. So compiler knows this is a parameter, i.e. constant. So it's later on it prevents users to change that variable. I'm just thinking if in C that's constant, if that makes sense. But if you are not familiar with C in Python, is Python I can't think about it. Something similar in Python. It should be. But I guess in Python, the way to think about is mutability, I guess. If it's with parameter, with this parameter, well, with parameter, that means it's not mutable. You can't change it. It's read only. Oh, sorry, I'm typing in the chat. I didn't see. Yeah. Sorry, I didn't read. I was talking to myself. I was talking. I didn't realize you were typing. Right. Yeah. I think in C, it's also not. I think even in C++ probably enforces constant in C, constant. I think in C it's probably not even enforced either. But I have to fact check that. All right. Let's crack on. 5 minutes break this up. So we come back to arrays, and the Fortran is very special in the way. Another very special feature of Fortran is it's column major. It's not a C, it's row major. It's column major. What does that mean is when you store a matrix in memory, it stores column first, then row. So it goes column by column rather than rows by rows. So, for example, a matrix from matrix of 2 by 2, the 2 by 2 matrix, it stores A11 first and A21. So the A21 is still, so it's saying it's column major doesn't mean it's so the 2 here is still the number of rows. So it's still second row, first entry. Okay. But it just stores that one first instead of storing the next instead of storing A12. So you still read this as row first, column second. So the first one is row number, second one is column number. Okay, this once it's column major does not mean you swap how you read the matrix. You still read the matrix as the same way you read, but it's just when it's stored, I stored column first, then rows. So the implication of this is when you need to loop through a matrix, we need to loop through the columns and the rows. So you put the column at your outer loop and row numbers in your inner loop. So that means every entries in the matrix is all aligned consecutive in the consecutive memory location. You don't have to go jump in different caches, which will be very slow. So if you do the other way, well, I guess the more conventional way in Fortran, it will be very slow because there will be cache misses. So be mindful with this. It's Fortran is column major. So initialization, we kind of touch on this. If you create you can start with a 1D array again, like NumPy, then you can reshape this array. But like NumPy, but not entirely because it's column major. So if we have this array 1, 2, 3, 4, 5, 6, when you reshape this 2 by 3, so it's going to be 2 by 3 matrix. It's not going to be 1, 2, 3, 4, 5, 6. It's going to store 1, 2 as the column, and 3, 4 as second column, and 5, 6 as third column. So this is the result. Because when you create a 1D array, Fortran takes this 1D array into a consecutive memory space. So when it reads, it's going to read 1, 2, 3, 4, 5, 6 consecutively, and then lay out them into the and lay out them in this required shape. So one end up with this. So just be careful with Fortran matrix that can shoot a foot. If you're not careful with the column major convention in Fortran, it might make mistakes and shoot your own foot. Accessing elements and slicing, nothing much to talk about here. It's just that's what you imagine. You give the correct index. Start with 1 by default. It's not 0 anymore. It's not Python. It's not C. Array slicing. It's like Python NumPy slicing. So I will not go into details about that. Just as what you would imagine. Although it is column major, as I've said before, you still read the matrix as the same way you read. The first one is row. The second index is column. Okay. Again, I can't emphasize this enough. Fortran is very nice with matrix and arrays and linear algebra stuff. Like NumPy, you have all this built-in functions, like so asterisk here is element-wise multiplication. If you want a matrix multiplication, there's intrinsic function provided to you, which I'll talk a bit more later. It's matmul. I think NumPy use the same function name. I'm pretty sure NumPy actually on the hood is just calling Fortran functions. Transpose, summation, so all the nice good stuff there. If you want a dynamic allocation, meaning if you don't know the size at the beginning, you can use this keyword allocatable. That means this matrix is size is to be determined. Then later on, you can allocate the you can allocate the memory for the matrix just by using this allocate matrix function, allocate function matrix with the desirable size. Another thing here, if you are familiar with C, that makes that probably looks very yuck here. Because you're going to assign a value to a matrix. So this is elemental. When you assign this, it assigns 0 here to all the entries in the matrix. Okay. If you allocate the memory for matrix, you do need to free memory. It's optional, happens automatically at the end of the program, but I think it's just good practice. So there's a summary here, indexing, how to slice matrix. Again, if you are familiar with Python NumPy, it is exactly what that is. So intrinsic procedures. One simple example, I think we saw this already, is like you have a built-in. The intrinsic procedure means like the built-in functions. For example, sum here, it can just sum a matrix, an array for you without actually even defining what sum is. And you can, the other intrinsics is minimum value, maximum value, absolute value, those nice good stuff. So Fortran has many intrinsic procedures. I just list a few. The most impressive ones are for array operations in linear algebra, so save you from writing big loops. So you imagine if you do this in C, you're going to write a for loop when you go through every index, the index of the array, and then sum them together. In Fortran, it's just one sum function. So that's what I mean. It's in C, in a Fortran way, you can just call a function applied to the array, and you just apply all the element-wise throughout the entire array. We saw this already. It has many intrinsics for linear algebra, matrix multiplication, transpose, dot product, so on and so forth. There's, I think, hundreds of them. And they all typically optimized by the compiler to use SIMD instructions or BLAS libraries. And BLAS library is rated in Fortran too, so underlying scientific computing, law of code is all written in Fortran. And law of code are also written in Fortran 77 as well. So when I heard people saying, "Oh, Fortran has already died out," so it's not. It's just so fundamental and underlying that you don't even notice when you use them. This is a few more examples here for matrix operations in Fortran. You can have reductions for collapse matrix into scalar or vector. For example, you can sum a matrix along the row or along column. If it's along row, it has the parameter here, theme, dimension, 1, that means summation, so result in a row down the rows. If it's 2, it's summation across the columns. Okay. Intrinsic function also supports location querying. For example, you can query what is give a great matrix 10 by 10. You can query what's the max value of this matrix, and it will return the coordinates instead of the value itself. There's element-wise mask in the where construct, which is handy sometimes. So it can give an array if you want to mask out instead of having an if condition. There's a where construct there, followed by the condition. That's one nice thing to have in Fortran. And I put it here. There's a nice construct, still concurrent. It's kind of like for loop, but if you know this for loop is independent, you can use still concurrent. What that means is tells compiler every iteration of this loop is independent, so you can do whatever parallelization is available to you, like automatic parallelize loop, spread across CPU cores, or SMD, and even for GPU, it can offload to GPU for multi-threading. I think this might require, this probably will require, if you use NVIDIA with Fortran compiler, this requires you have an extra flags there. So this is syntax. Just instead of saying the do for loop, you do concurrent. So yeah, just one example here. You do need to make sure the loop is independent. If, for example, in this one, if the first iteration is dependent on the last iteration, this will cause the problem because that's not independent. But if it's independent loop, you can use do concurrent. Okay. So that's basic Fortran syntax. Modules. I'll talk a bit more about like program structure, and I'll start with modules. Modules are the fundamental building block of modern Fortran. So basically, it's kind of like header file in C. It describes the interface. Then everything writing modules. Then you can use in other source files. So that creates a namespace. For example, there's one module as the format of using module. You start with module keyword, what this module is, which module you want to define the implicit none here. It usually contains 2 parts. The first part is just all the parameters. And once you've done part 1, the good practice is use the word keyword contains to follow up with part 2, which is going to be the functions, procedures, subroutines related to this module. So how to import the module? You can import the module, just the keyword is use. Okay. I said before, implicit none is usually on top of the program, unless you have a use module. If you use module, you need to use module prior to implicit none. And then once you use the module, you can call whatever the variables and the defined variables in that module and functions from that module. If you just want to use certain parts of the module, you can use, then only is the keyword to import certain part of the module. Okay. Any questions so far? We will sort of compile all this together in the handout or for live demo. Procedures. Fortran functions is called subroutines. It has functions as well, but it means different things. Functions calculate and return a single value or array usually use this in expression. So you have a function. So do I have an example here? Yeah, C equivalent is yeah. So you have a function that returns value, and then you assign the value to another variable. Subroutines perform an action, and it can return multiple values via arguments. So when you use subroutine, once you define the subroutine, you use call this keyword. For example, in this code, I define a subroutine, transform the Cartesian coordinates to polar coordinates. It can return you can return as many variables as you want, but they're through the arguments. So in here, I changed this theta variables in the subroutine. You have to end the subroutine as well. Now, if you want to use the subroutine, how you invoke this is use call. Use the module to in your main program. You use this module and then call the subroutine with the call keyword. I'm scrolling through this fairly, I guess, quick because I don't want to dwell into this into the language program concepts too much. So this is really just kind of for a refresher. Functions is different from the subroutines. You need to have a result, a sort of return what is returned for functions, and it has to be a single value or a vector. And when you use the function, you can just you don't need to use the call. You don't need to use the call keywords. You can just use the function name, like this one. Just use the function name for it. Another safe feature of Fortran related functions is it's recommended that you put the intent for all the variables. So its intent can be three cases. In means it's read only. Out it's write only. In out is you can read and write that variable. So that prevents you from accidentally modify the variables that is not supposed to be modified. Okay. So Fortran pass everything by reference, similar to passing pointers in C. So this is why the intent is so important. If you pass variables to a subroutine without intending, the subroutine technically has the power to change your variables in the main program. Modules and interface. This is good practice. You should put all your place all your procedures inside the module, so they have a clearly namespace, and then you can later use this module in your main program. So I have the bad example and the good example here. The bad example, if I have if I call this external sub function in my main program without using module, this is in C, this is basically equivalent to, without header file, I'm just going to link the file. I'm just assuming this is somewhere in the file that I'm linking. So you don't know what this, if you pass the different data type, it will not be detected at the compilation time. It only will crash at the runtime. But if you put this external sub somewhere in the module, then you use that module. See here, strict. I put this one in the module, and then when I use this module, when I use this function from the module, the compiler will check if it's the right if it's it will do a sanity check for me to see if it's input is all type matched. So this is basically in C. It's you have a header file for your for the functions that you will use from different files. It also has public and private in variable keywords, so that dictates that if the variables can be used outside of this module or can only be used inside the module. Reasonable, just as what you would expect. So some tips for numerical for scientific computing is always use implicit none in every program unit. Be explicit about kinds for reals when you need it. Use array syntax instead of manual loop. This is what Fortran's for you. It just provides all this building intrinsic functions that save you from writing manual loops. Avoid uninitialized variables. Compile with warnings, or the standard good practice. Prefer allocatable over pointers for ownership and performance. We didn't really talk about pointers. But it's not really a C pointer. Fortran pointer is not really a C pointer. You need to. So I didn't put it here, but I can say very quickly say that in the Fortran pointer, you do need to have the type and the initialize pointer with the correct type or with the type at the beginning. So it's not the C pointer. And you don't really use. I've been managed to avoid using pointers in Fortran. So now I'll talk about a bit more project layouts and a simple build. So usually when you have a project in Fortran, I guess the standard way is you have a source code in one source file and you have a build directory. So when you build, compile code that's compiled into the build directory, kind of like C program. Good standard layout, which we will see this in the practice later. Fortran compilation. I think this is the last part of this quite short syntax overview. So pretty much like C program, you compile, you have object file, you have your source file, you compile your object file, and you link them together, and then you can run your executable. The main difference here is Fortran handles interface and the dependencies differently. What I mean this is, let's look at the format first. Fortran, on top of the object file, Fortran does not have the header files. How it handles the different modules is provides this mod file. So when you compile a module file, it produces two files. One is executable, one is this mod file, which is kind of like header file, what tells you the dependencies for this file. So when your main program says I'm going to use this module, the compiler will look for its mod file to check the types and stuff. So what that implies is when you compile a Fortran code, the order matters. In C, if in C, say if my main uses function from the utils file, the order doesn't matter. I can compile main first and compile util second. But in Fortran, you need to compile the utils file first and generates the mod file, and then compile the main file. So that is something keep in mind. Well, so another example to say is, in C you can say GCC, and if you have two files, you can say GCC file 1.c, omen.c, utils.c, and the -o with your executable. In Fortran, you do need to put the utils.o before main.o. That's the major difference in Fortran compilation. Okay. Any questions so far? I think that's all the review syntax basic programming review that I intended. Plan for
Fred, there
yes.
are questions in the chat from Peter.
Right.
He was asking for an example.
Yeah.
Yeah.
Thanks, George. Yeah, I'll read through because I'm not sure why today all the chats does not give me prompts in the. So sorry about this. There's usually the chats will give me a prompt saying there's a chat, something in the chat, but it's not. It's weird. So sorry, I just didn't see it. Peter, could you put an example module load and compile system with flags so that do concurrent automatically works if I have an interactive PBS shell with more than one CPU? So that flag I think is more for GPU. You need to specify the GPU flag for NVIDIA compiler. I think in GCC it's picked up in I think that is picked up from the old different what do you call the optimization flags. But yeah, we'll see that in a second. Just checking. I was saying that type checking with intent only works inside the module. So what I've said there is, if you don't use module, the compiler will not know what type is when the compiler says, oh, I have this function. I assume this function will be provided to me later at the linking stage, because you have compilation and linking. At the compilation time, it does not know what's going to be linked. It's just reserved. The block say, okay, this is going to be provided to me at linking stage. At this point, I don't care. And once it's linked, then you're going to run the code. But if you use module, and then what will happen at the compilation time is the compiler will see, okay, this is provided from module, then I'm going to go to check what's in the mod file and what type is specified there. So if it does not match, it will just stop at compilation time. Instead of later, if it doesn't, instead of in the first case, it will crash at runtime because there was no compilation check. Okay. So I hope that answers that question for Peter. I'm just see if there's more questions. Once allocated, the dimensions are fixed. You should be able to check out to change that to change the dimension if it's allocated. Function can also modify, or they can only return. This will depend on the parameter if it's mutable or not. So yeah, they can modify if it's not. Also, how we optimized when you say that lookup functions malloc. do you how optimized would you say the lookup functions are? Or do you not recommend using the except with stuff? I think all the built-ins intrinsics that all fairly well optimized. Right, so that's all the question for now. I'm just going to quickly go through this example that you guys gonna see in the code. It's simple Monte Carlo methods that will approximate pi. So basic thing about you just scatter a hand of rice, and over the first quadrant of the circle, if just then count how many is within the circle and divided by the entire number, and that number is approximation of pi. So the code here is the key part of the code is you sample many numbers in large number of points, both x coordinate and y coordinate, and you just check if it's within the first quadrant. And if yes, then you increase the count number. Then once you finish all the counting, and then just divide it by 4. That is pi approximation. Okay, so yeah, I'll leave you to rate this if you're still not very clear, or ask me questions. In the meantime, I'm just going to show you the code. I have it. So Matthew's question, I will show you. Okay, I'll show you how to load the compiler again. Let me just use this. So what the code we have here, I'm going to put in VS Code here. So I'm using VS Code. So some of you may use this. Some of you may just use Unix. If you don't have VS Code, you just use terminal. That's fine. So what you can do with, if you have NCI account, what you can do is you can go to, actually I'm just going to use my terminal here. So go to your home directory, and you can just git clone that repository that I shared with you in the chat at the beginning. I'll just put it again, just this repository. Codes, and you can just clone this thing, copy this in the clone into your home directory. All right. The intro, we can go to the source file. So it has some source file. So it has 3 source files, the main file, and the main file is, let's have a look. If you want to have a look, I'll use my VS Code. So this is my main file, it's MPI code, which I have the main, this program, again, I'm using some functions called the Monte Carlo mode. This is the module. I'll show you this later. I'll walk into this later. And I'll use MPI. So when you run MPI code, when you code program MPI in Fortran, MPI is provided through module. Okay, so you need to use use MPI, and all the MPI functions in Fortran is very nicely just subroutines. So you say all the MPI code, I just use core MPI functions. And so after you use import the modules, you can don't forget this implicit none. Define variables. I will not talk about details about MPI because that's not the focus of this session. So what this basically does is main. This is basically saying but I guess it's probably I should say some or two sentences by MPI. What it does is it's distributed parallelization. Basically, it tells how the X number of processes that you requested through your PBS job scheduler, and every processes run this code simultaneously. So for example, MPI init here is just for init MPI environment variables. MPI com rank is just get how many processes you have, and com rank is gets what is the rank of this processor. So if you have I think we'll require probably 4 processors for this run. So you have 0, 1, 2, 3, 4 processes, and each one have its own rank. And MPI, so the com size is the entire size of this. So it stands for communication size, stands the entire size of the communication. In this case, if we request 4 processes, the number will be 4. We just have an MPI barrier, so it's basically a stop line. So because we're going to start timing. So for each processor, so I have if rank is 0, so I don't want to print the same statement 4 times. So I just have an if condition here. If rank is 0, then I'm going to print the n is the total number of sample points. So starting simulation with n equals this number, and then for each processor for each rank, I'll call this compute MPI function, which is called from Monte Carlo mode from this module. Okay. And MPI reduce, then I want to sum it on sum or this sum the count throughout all processes. Again, then once I get that local count, got the summation across all processes, I can calculate the approximation. I do this print with only for rank 0 because again, I don't want to do the same print statements for 4 times, and I finish the MPI function with the MPI file lines. Okay. So that's okay if you don't understand too much about MPI, but this is just a this is just a de facto parallelization tool, which has native support for Fortran, as you can tell already. You just literally just use a module and call its functions. Okay. So this is the main, and for this actual calculation happens in the help routine here, which I call Monte Carlo mode module. I have 2 versions, one's CPU version, one's GPU version. Look at the CPU version first. What it does is it just calculates that part that I showed you before, sampling random points, and calculate if it's within the first quadrant of the quadrant of the circle. I'll have you read through the code. It's not so important for you to go through the code actually. I just want to demonstrate that how I just want to use this as demonstrated how to compile and run a Fortran parallel code. Same function, help function, Monte Carlo mode. I have a GPU version as well, which provides me the same function, same module. Within GPU, accelerate this with OpenACC program model. Again, this is if you're familiar with OpenMP, this is just GPU. You can think about this GPU version of that. So this is this does the multi-threading through the pragma. So this is the pragma for ACC, then basically just parallel the loop. Which loop we're going to parallel the loop for the random sampling. So yeah, I have two. Basically, yeah, simply 3 files. One's main file. The main file has the main routine written in both CPU and the GPU. And then when I compile this in my Makefile, I'll show you in a second. In my Makefile, I have 2 targets. One CPU targets compile the CPU code, and GPU targets compile GPU code. So the CPU targets just compiles the mode CPU mode and link this mode with the main. GPU target compile the GPU code and link that mode with main. Okay. The compilation flag is for CPU is 03. Hyphen module is write this into the build directory. In the GPU flag, well, what we're going to do here for GPU is because just as on Monday we have the latest H200 GPU commissioned, so we're going to compile on the latest GPU available on Gadi, and with that architecture is with flag CC90. OpenACC requires them. It's not necessary, but for simplicity, I have a managed memory with Intel's compiler. I'm using OpenACC. Okay. Other than that, it's just some basic Makefile things, which I will not dive into the details. So you can do the same with me here. Once if you have a terminal. So I'll show you the tree here. Oops. So this repository have all the documentation there as well, which is not really useful. But in terms of source code, this is my source code, and I have in the source code, and I just type make. It will give me error for GPU part because the login node on Gadi is not a GPU log, does not have a GPU. We will later request an interactive job and then compile on GPU. But for now, if you do make, it will make for CPU code. But will not make for GPU code because there's no GPU. So what's going to create is a build directory. Once you done make, you have build directory. They have 2 directories now, CPU and GPU. Probably for CPU, you have your what I mentioned before. You have your main object file for main file for your main, and you have the mod file for this helper function and object file for the helper function. And linked together, you have MPI CPU. Okay, so now we're going to run this we're going to run this CPU MPI code. What we're going to do is module load the MPI. Let me module purge first. Just make sure I have a clean environment. Module avail. So module load. I'm going to load the OpenMPI, this version, and this will give me which MPI port is this one. And what does that mean is MPI port, this compiler. I just do this again. This will use Fortran, okay, under the hood, but with MPI library loaded. So this enables in the Fortran in this code, this enables my program to find the MPI library and use all the MPI library. Okay. So MPI is through library, so you do need to load that library. Okay. Let me actually. Yeah, so sorry. I made a mistake there. When I was compiling previously, I was compiling with the Intel compiler that I loaded before. Now I'm gonna make a clean and recompile this again. Sorry. Let me change one thing here. I think. CPU maybe. Yeah. So it's this so this flag. Sorry, what I changed there is I have a mistake in the Makefile. So in the CPU version, it's gonna take J as the flag rather than module. So I put it wrong flag there, but you can change that. So once again, it's gonna have error, but this is error related to the GPU, which is expected because we don't have a GPU on the login nodes. So once you make this, now I remake I remade the executables. I can go to CPU, sorry, build directory, CPU. And I'm going to run with the MPI run, number of processors full, and MPI full. So it gives me the results. Okay. This on login nodes is sort of not really a real workload. I did it because there's only 4 processors needed. If I'm going to do a real workload through job scheduler, in the repository you can find this. Do I have it here? That's fine. In the repository, you will see I provide you with a CPU job scheduler there. So CPU. Open up the CPU job scheduler. I can request 12 CPUs with this much memory around 5 minutes. So they are the standard PBS flags, just about requesting resources. You do need to load OpenMPI again for the job scale within this job submission script, because it's going to send the job to the computer node. Whatever you load now in login node does not transfer into computer node. So you need to load the OpenMPI library again, and then you run the code with MPI run. We can use 12 CPUs because we request 12 CPUs there. So let's submit this job. So the job is submitted. Then we can create the job with qstat. Once it's running, it should finish very quickly. Then we can see the results. Okay. In the meantime, I'm going to show you how to compile this on GPU. Okay. Let me open a new tab. Go to Gadi. For the GPU code, because I've been saying this a few times. We don't have login node does not have GPU, so you can't compile GPU code. So what we're going to do is we're going to request this. If you log in Gadi, you'll see this news. We'll have the new H200 GPU loads available. So we're going to compile the code. This latest GPU on Gadi. So how we do this is we're going to request the GPU3 interactive job. So qsub -i. I'll clear the H put in half so you can see better. Let me know if you can see clear here. So qsub -i -q -s stands for interactive job -q for the Q for this latest GPU. We use GPU Hopper. It's the Q name. Because it's a Hopper architecture project. I need to use my project. You use yours. You probably don't have access to this one. Overtime. I'm reading this from NCI website. You can find this from NCI website as well. I noticed a few more messages. I'll have a look in a second. NCI. So in the user guide, if you go to user guide, just search interactive. Job submission. Something like this is probably here. Yeah. You can find me here. I'm just so this is let's just say half an hour for 10 minutes. 10 minutes, what time? We're going to book for entire GPU nodes, which has 48 CPUs and GPUs. 4 GPUs. So one Hopper GPU node has 4 GPUs, and memory is 1 terabyte memory, so 1,024 gigabytes. JobFS, it's to the file system on the node. That's kind of unnecessary here, but we'll just put it there. Now storage. Do I need this one? It's in the home directory, so probably I don't. Scratch 2. And the working directory. So send this one, wait for the job to start. Once this job starts, let's check the CPU job. It's finished. It's the queuing one is the GPU one. Now we can have a look at the output. Tells me this is the output for that job, for the 12 CPU job, 12 core CPU job, Fortran. While it's loading, I'm gonna see the questions if there's any. So could you describe again what needs to be done to compile for a GPU? Thanks. For compiling GPU, so assuming you have an OpenACC acceleration written for your Fortran code, which is not that well, which needs to be work. Once you've done that, so in the Makefile, you need you need a GPU to compute to compile. So that's what I was doing. That's what I was just doing. Just request GPU. In the Makefile, you need to specify the architecture of the GPU and specify the ACC pragma is used. But this depends on NVIDIA GPU like that. If it's not NVIDIA GPU, then it's going to be completely different flags and compile because you're going to use different compilers. All right, so now we landed. We have a GPU now. Let's see what we will need to compile GPU code. So Peter, this is probably what I'm going to say now is probably the most important thing to for your question is on Gadi to compile GPU on Fortran, you will need to compile this. You need a couple more things because you need a GPU compiler for Fortran, and this is provided through module avail NVIDIA SDK, yes. NVIDIA HPC SDK, so there's a HPC developer package. Use the latest version because this is the latest architecture. So you need to module load this one. They will give you a warning. I just ignore it. Module, and on top of that, you will also need the module CUDA library as well. So you need to module build CUDA. So latest version is CUDA 12.9.0. Follow that. Module load CUDA. Because it's MPI job, even it's GPU, but it's an MPI job, we're going to module load MPI as we did before. Module load OpenMPI same version 5.0.8. Okay, now we'll check this with module list. So we have all these three things loaded. So what does that? So what compile is now? So if we do module show MPI, which MPI port? It tells me from the wrapper is MPI port from OpenMPI. However, because we loaded the NVIDIA HPC SDK that package, now your MPI Fort wrapper is wrapping around NVIDIA Fortran as a compiler instead of G Fortran or Intel Fortran. Okay, so the compiler itself on the hood is NVIDIA Fortran with MPI flags preset for you. Okay. Now I go to this. Now I go to my source code, and I'll make again. And this will compile. Now this GPU code compiles. So they use MPI F90. So the thing is, if you do, well, sorry, what I was thinking. Yeah, if you do module, if you do MPI F90 compiler show, it gives you the same thing as it will show you the same thing as what I did before, MPI Fort show. So when you use NVIDIA compiler, NVIDIA compiler for GPU for compiling Fortran on GPU. It's actually then MPI F90 and MPI Fortran is the same thing. So you can use both. Both are the same. Both the wrappers wraps are the same thing, and then you can compile them with MPI F90. Okay. With that, now I can run the code. Because it's MPI code, so it's even if it's a GPU, it's still gonna be MPI run. I request how many CPUs? Let's see, 40. I think it will be 4. Because you have 4 GPUs, so I'm gonna request 4 CPU, 4 cores, and each one gonna offload to a GPU. Build GPU MPI GPU. And then GPU result, GPU code results. Similarly, if you want to do this, let me get back to my login notes. If you want to do this through job submission script, I provided the GPU job submission scripts here for you. But this one is through on Volta though. I can change this to GPU output. Change the memory to okay. So similarly, when you request GPU job, the GPU node needs to load all these libraries. That's what I did before. I updated the version because I'm running on the latest version of GPU. Those ones are the ones I set up for previous version GPU. So you can load all these libraries and then you run the GPU job. So qsub. My coupons, sorry. I need to change this to a different project. Right, and job is queued, and it tells you it's running on the GPU hub. So then we'll get the same results as what we had before. I hope that answered the questions. So I just want to be a sensible range of possible JobFS values. So the JobFS is not the storage, it's not Scratch library. I think we finished now in the main main session. I'm just gonna take some questions and answer some questions I didn't answer before. Now for Peter's question, perhaps beyond the scope for today, but what would be the sensible range for possible JobFS values? So the JobFS is the file storage, file system on the node. It's not the Scratch, it's not GData, right? Just be clear with that. It's not the Scratch storage space. It's literally the file system on this node. So what it means is you have a temporary access to that file system. So you can use the file system as long as you are using a node. So as long as your job scheduler terminates your job, then you don't have access to that JobFS. So I said be unnecessary information here. What does that mean is you can request, if you request a node, entire node, so you may just request entire JobFS, which is going to be different. I'm not sure how much is on Hopper. I have to check the number, but usually just probably 1 terabyte or something like that. So you can request the entire JobFS because there's no harm there. If you request the entire node already, the only thing is, the benefit of using JobFS is if you have many I/O in your job, you can write thousands of files. Instead of redirect, write all the files back to Scratch, which is gonna through a network because they're separate, right? Like they are separate machines. You can write into JobFS and then as part of the workload, and within a job, FS table all your file into table all your output in the job in the JobFS, and then transfer them to Scratch as a much quicker way than do many IOs directly to Scratch. So that is the workload around it. So answer to your question, if it's simply, you may as well just request the entire largest number of JobFS of node if you are using that node. Okay. Hopefully that kind of makes sense somewhat. Are there more questions? So we can have a look at the JobFS from the manual here. So let's go to what with queue types. Queue structure, queue limits. In queue structure. So for each queue, it corresponds for queues that correspond to different hardware. See the Grace Popper one. I don't think it's updated yet, but see the GPU Volta, this one. It has 480 gigabyte local SSD disk. So that means for each node, you have 480 gigabytes for JobFS. Okay. All right. Are there any further questions? Otherwise, I'll return the day for you, and thank you again for joining this session. And if there's any feedback, please let us know. Again, this is the first time, this first offering of this material, so all your feedbacks are valued. Thank you for your time and patience. Have a good day, everyone.